So hi everyone, and welcome to this video. My name is Kyriakos Ikonomou, and I'm the author of the ARS course from eLearnSecurity, which is basically a course about reverse engineering software. Some time ago, eLearnSecurity and the Ethical Hacker Network joined together in order to promote this course with a very interesting challenge, of which I was the author. Through this video, we're going to see the protection mechanisms that are implemented by this challenge and how we can bypass them in order to successfully solve them, solve the challenge. So let's start. Let's just run the challenge once. Press any key. We see that the data validation is in progress, and as we can see, we get the message not yet made. So let's load the challenge to Oli. We are at the entry point. We can press Ctrl+A in order to analyze the code. Let's take a look at the debugging options. As you can see, I have instructed the debugger to process all exceptions apart from memory access violations occurring in kernel 32. I'm doing this because I want to see if any kind of exception occurs during the execution of the user code. So I don't want to automatically pass it to the exception handler of the application. I want the debugger to stop and let me examine what's going on. So let's run and let's see what happens. We need to click once to let the execution continue. We see that the execution stopped here because of an interrupt-free command at this address here. So let's see what happens. I'm going to run again. And we see that every time I run, this is interesting. You see that we had an access violation on executing instruction on this address here, which is not a valid address inside the virtual address space of this process, and basically at any process in user mode, because as you know from when the most significant byte is 80 and above, we refer to the virtual address space of kernel. So let me start the application again. Run again. And let's start just stepping over instead of just running without having control of what is going on. We see that EX is going to be used to perform various operations with values that are stored in these addresses here. You see these 4 addresses and then 4 addresses again with OR, and here we have addition, OR, subtraction, and exclusive OR. Okay, let's see what happens. We also see that here there is an addition between a constant that it's stored in this variable here on the stack with EX, and then EX is going to be used again to OR the values in this address here. Let's continue. We see that we return in this address here, and here is the call that calls this function. We also see that this instruction here is going to increase the value stored at the top of the stack by 1. So let's see this. Increased by 1. Then jumps up and then returns. So this is the return address, and we saw that this function increased the return address by 1. We see here something very interesting. Notice that the disassembler is not able to correctly disassemble these instructions. So let me select this block, do analysis, and treat these bytes, let's say, as commands. We can now see something, let's say, a little bit better, but not really. You see that this is going to jump in the middle of the next instruction. So let's press F8. Now the instructions are cleared. So you can see that there is a lot of anti-disassembling obfuscation. So let's enter this function here. We see that the return address is increased by 1 again. Then the function that contains this strange code here that makes the debugger stop every time is going to be called this function. So let me just keep stepping over. And then we return to the address that was previously increased by 1, and then calls another function. Again, we see that this increases the return address by 1, then calls the same function that we saw what it's doing. So if we enter here, we can just label we can say int. We call this function as int3, just to know what happens, just to give it a name. We don't know yet what happens here, excuse me. So let me go back, and we see that the return address is going to be again increased by 1. So this function in total, before returning, increases the return address by 2. First time here, then calls the int3 function that we just named, and then increases again. So let me call this function incorrect1. And then we see another function being called, and see what happens. It calls again the same function that contains the interrupt3, then adds 4 to the return address, and then subtracts 1. So this function is going to actually increase the return address by 3. So we can call this incorrect3 as a label. Okay, we see increase the return address by 4 and then subtracts 1 and then returns. Then we see another call to another function. We see that increases by 3, calls the function that we know there is the interrupt 3, and then increase again by 1. So this function increases total by 3, the return address. So I'm going to do increment by 4, sorry. Okay. We know that happens in here. And return back. Let's see now the next call that is going to be performed. Let's see what happens. We see that first it saves all the registers. Then it's going to retrieve basically the return address from the stack. You can follow disassembler. This is the return address. Now the code is obfuscated, so you don't see the code before. We're going to fix this in a while. Subtracts 32, zeroes out EDX and ESI, and starts reading from where EAX points, from here. It starts doing some calculations. So what we can do now is that we can put the breakpoint here, run until the loops finishes, and then we see that the final value is stored in ESI, which is going to be saved at this address here. So it's like calculating a checksum for a block of code. So we're going to label this function checksum1. And as we can see, you can keep some other notes here. At address 41 B2 C0 store checksum1. Okay, so let's go back. Then calls another function. We see that it again saves all the registers. Then retrieves the value that was calculated before, and then stores the value with another one. Remember these values, this, and this, that were involved in the function that caused the interrupt 3. So anyway, it does some calculations between those values, among those values, then XORs the return address with that final result, add to that result this constant, and then tries to return to that address there. And this is where things get messed up. So we need to identify what really happened. We see we don't have any active breakpoints to mess up with, for example, the checksum that was reading code from memory. We also haven't done any code modifications, and we didn't see any debugger detection trick. So what we should do is to go back and examine better the function where the interrupt 3 is located, and see if we can find some clues from there. You see, if I just try to run, we have memory access violation. So let's run again. Let's view function names by type. You see here now Oli has kept the names we put to those functions, so we can directly go to this function here. I'm going to put a breakpoint. Also, we can set the breakpoint hardware run execution. Run the challenge. And we stop here. Alright. Let's start now and see what's going on. We see that this function here is going to make a call to the set-handle exception filter API. And sets this address here as the top-level exception handler. You can follow in Disassembler. So let's try to do something different. Let's go to options and let's instruct the debugger to always pass the interrupt-free breakpoints, like the software breakpoint exceptions, to automatically to the application, so that they're going to be handled by the application and not by the debugger. So let's just run with F9. We see it says that the debug program was unable to process exception. Let's press Shift plus F9, trying to see what's going to happen, and we see that the application is terminated. Our breakpoint is still there. So let's run again. And let's explain what is going on in this function that messes up with the rest of the execution later. So let's start stepping over. We see that the function reads the byte that is located in the return address. Here it is. Then keeps only the last one, the one I read from EX, and then calls this API. So basically the trick is somehow related to Windows internals. What really happens is, according to the documentation for this API, is that when we set our custom exception filter to be the top level filter through the set-handle exception filter API, there would be a check to verify if the application is currently being debugged by a Ring 3 debugger. if the application is being debugged, then the process is going to be terminated. Otherwise, the execution will continue from the registered exception handler. This is the expected behavior, and sometimes it is used as an anti-reversing trick just because it natively works against Ring 3 debuggers. In order to bypass this, there is a simple trick that we can do. We can go to the unhandled exception filter API and modify the code so that it always returns to the caller a false negative that the process is not being debugged, so that the execution will continue from the exception handler and it will not be terminated. So here is where the magic happens. It's going to push this constant that belongs to the debugger detection and then call the ZW query information process that will directly go, that will then pass the execution to the kernel and is going to return a specific value. So we can set a breakpoint here. Remember that now we automatically pass in breakpoint exceptions, software breakpoint exceptions to the application. So let's run. We see that it's going to call, then checks here if the call was correct, if the function didn't fail at kernel level, and then compares EDI with this value here. If the process is being debugged, the value stored in this variable is going to be this one. So what we can do is patch this API to store 0 to that value. This jump is going also to be executed because the flags were already set correctly by the previous function here, by the previous instruction here, sorry, while testing if the empty status error was success. So we're going to substitute this value FFF now with 0. These jumps. So now the application will not be terminated, and we see that it calls here the exception handler. Increases the instruction pointer by 1. If you see here, this is the beginning of context structure, and at from the beginning plus B8 it is located the ape register. So it's going to increase it by 1 in order to continue the execution from the next instruction, so that it will not try to execute again the interrupt 3. Return back. we can go to see the names. So let's place a breakpoint there and just run. So you see everything went okay, the application didn't crash, the exception was handled by the application. So let's see what happens. Again, we see that we have these constants here, which now we can start taking some more nodes. So we basically need these values here. So let's call these these are not really constants, so say they're variables. Excuse me for the terminology sometimes. I'm not a native speaker, so let's call this variable seeds. Okay. So it's going to add or subtract, or anyway, it's going to do some operations with every variable of these that we just saw is going to do a different operation. And in EX, as you remember, there is the first byte that is in the return address. This is it, FF. So it's going to do that. Let's see here. These are the constants. You see how they are modified. And then this is where the magic happens again. You see that it retrieves the exception code. This is the exception code for software breakpoint exceptions, and is going to add it to this value here that's already in EX, and then it's going to perform more operations with this result. So let's see how this changes again. Take a look at these values here. You see, they changed. That increases return address by 1 and returns. Good. So we know that here it calls the increase return address by 1. So let's try to clean a little bit the obfuscation. We know that the next byte is junk. Actually, this is by 2. Okay. So we need to rename this. Okay. So the next 2 bytes are junk. I'm going to knob them. Then we see a jump that is going to skip 2 bytes, so we can knob the next 2 bytes also. You see how the code now starts to clean up. Then it calls this function here, and this is the one that increases the ret address only by 1. So I'm going to label this incret 1. So I know that the next byte is a junk byte. I'm going to try to analyze again the code. Then we see that it calls the incorrect 2, so I know the next 2 bytes are junk. Can also verify this. See, first increase here, second increase here, then jump and returns. Then calls the increase 3, so I know the next 3 bytes are junk. So I'm going to clear them. Then calls the incorrect 4, so I know the next 4 bytes are junk. And then calls the checksum1 function, as we saw, that calculates a checksum. And then calls this function here. So let's see what happens. We know that every time a function that increases the return address is called, also this function that contains string is called. But now this is now fixed because we patched the function. Okay, so let me just start. Okay, I have the breakpoint here, we don't need it anymore. And we see that we had another access violation executed at a different address. So I'm going to go back. And let's start again. Let's patch the handle exception filter. Breakpoint here, run. Return. Okay. So let's clean again. We see that we can automatically do it from here. And analyze again. Okay, so this jumps 2 bytes. Then here the first byte is junk, so we nop it. The next 2, the next 3. So let me set a breakpoint here, run. Let's remove the hardware breakpoint from here, run. So it calls the checksum1, which let's enter the function. It's going to start reading from this address here, basically, and perform and calculate a checksum. So it basically calculates a checksum for this area here, probably to see if there are any code modifications. Then calls this function here, that is going to use the previously stored values. You see here should be stored the checksum 1, and it's going to check if by doing some calculations with the previous variables calculated through the function that contains the interrupt 3 and the function that calculates the checksum for that code area is going to be correct, So we see that adds this constant to the return value and then returns to an invalid one. So this means that we shouldn't do any code modifications, otherwise we're going to mess up with the execution flow. Or of course, if we know what should be the correct value here, the correct result, then we can just pass the binary, so it will always return to the correct address. But the problem is that if we patch the binary, then we have also to ensure that the area where we patch is not, let's say, involved and to check some calculations. So what I'm going to do is use the stack and see if we can find anything interesting. Not here. Or what we can do is just go back to where this function was called, and we can directly set the hardware breakpoint here. So we won't alter anything, so just set the hardware breakpoint here and restart. We forgot to patch that API here. It's very important. You can do it directly from here. It's very important so that that trick is bypassed. Okay, so now we directly stopped here. So let's enter. So this is the value that the checksum, this one, has at this point, which is 3C3 DBED4. Okay, and we see the values of the others and doing some calculations with the value stored in EBX. If we follow in dump, we see these four constants with the actual values. Then it's going to XOR the return address with the value calculated in EBX, and then it's going to add this constant. So if we follow in dump, this is the return address at the moment, and then add that constant, and the return address becomes 4017FF. So this is where we should return if everything goes fine. Okay, so let's keep executing. We see that the next byte is a chunk byte. So we can note this. Then calls the increase the return by 2, so we know the next two are chunk. So I'm going to set a breakpoint here and run. Okay. So the next 2 bytes are junk again. Then the next junk again. Then you see that here the next 2 are junk again. Then the next 3, then the next 4, and then calls again the checksum calculation function. Then we see that after this the next 3 are junk again. So let's just press a breakpoint here and run. We see that again is going to get the return address, subtract 32, and it's going to calculate now the checksum for this code area here to see if there are any code modifications. And then it's going to call this function here, which is going again to calculate the correct return address again, which won't be the correct because we messed up by patching the code to clean up the obfuscation. So we can label this function here, calc ret address 2. Because as you can see, there was another call that was doing the same. So what we can do is just set a breakpoint hardware and execution here, restart, so that we arrive at that point without cleaning any code from obfuscation, so we will not mess up with any checksum calculations. We will need to go and patch the trick regarding the handle exception filter, and ensure we don't have any breakpoints, software breakpoints left, and run. Okay. So you see it's going to call this function here. This is the first call, the first function that is involved into calculating a correct return address by using the values calculated from the checksum of previous code already executed before, just to see if there were any modifications and other variables. So we can label this function calc ret address 1. You can just step in. Okay, let's run again. Now we stop here where the execution was messed up, and we see again now that we have a valid address as a return address, and the execution continues from here. And then we see there is a loop looping up here. Then the next byte is junk. Then the next 2 bytes here. I'm just cleaning again just to show to you how the original code was looked like. we see that there are checksums involved that check for code modifications, so we shouldn't do any of them. But now I'm just cleaning for you to see how we can clean this kind of obfuscation and see the real instructions. And we see that when the execution enters here, the real return address is where this one jumps 4018. Okay, let's clean here. Okay. What I'm going to do is to go back . Let's jump. It jumps here. Then all this happen again. Then again the code checksum. And every time we see that it calculates the return address, which is the one we saw before. Here, and then jump again up and do the same loop again. So we cannot modify any of this during this loop here. But what we can do is to set a hardware breakpoint after the loop has finished, so we can just directly stop here and restart. So let's go and patch the handle exception filter trick and run. We'll do the first break here, the second here. We see that if we step in, calculates the correct return address every time for the loop. So every time the return address from that function is dynamically calculated. So it always checks if there are any code modifications here that we have used in order to clean up the obfuscation. So let's run. We can remove the hardware breakpoint from there. We don't need it anymore. So we now stop after the loop. You see there is a call to this function here. Let's enter and see what happens. Jump here, saves all the registers, calculates again, calls again this function here that calls the interrupt free trick through the handle exception filter. So we know that the next byte is junk. Let's analyze again. Then jumps up. Let's try to analyze all of this. Then here again the next one, then jumps here, then the next one is junk, then jumps up again, the next one is jump, the next one is junk, jumps up, the next one is junk, jumps down, again the next one is junk. So we try to clean up a little bit to reveal the real algorithm. Let's clean this here. Let's clean the code here. So basically, where we see this function being called, we just clean the next byte. So we'll try to find all those locations inside this function. And just clean the obfuscation. Okay, the code now looks much better. So let's press breakpoint here. Let's see what happens now. We see that it reads the address of the process environment block. Adds 8. So let's see what is there. It's, you see it's the image base of the process. Then it jumps up, reads that value, passes also this value to edx. Then reads the pointer to the P header, which is stored in the offset 3C. You see, D8. So calculates the value of the start of the P header, adds 100 hex, so arrives at the beginning of the characteristics of at the beginning of the first structure that describes the first section. This is the sections table. So let's continue. We see that it reads the size in memory. Then adds to ex4. So it takes the relative virtual address, actually ex points now there, but now it's going to read it to ebx, the relative virtual address of the first section. Then performs a calculation to calculate the full virtual address where the first section starts. And it reads, it starts reading d word by d word. Let's clean this. And starts performing again some kind of checksum calculation. But this time, you see now it increases the pointer. It loops for the entire first section and calculates a checksum for all of it. And when this loop has finished, the execution is going to arrive here. You see the loop that loops up. So we can set the breakpoint here and let it run. Until we break here. You see, if I put a breakpoint on the loop, it stops. Let's run. We want to let it loop until okay. So it calculated checksum for the entire first section and saves the checksum to this variable here. So I can do store full first section checksum. Now I have done some modifications, so because I was patching here, so the checksum will not be correct, but we know that it's going to be saved at this address here, and then jump here and here, and so this is where it's going to return. And then it's going to, as you can see, look for this file here. So what we can do is set a hardware breakpoint here and restart everything. Patch the handle exception filter trick. We don't need this breakpoint anymore, but anyway. So we arrive here. Everything went fine, no crashes, because we didn't do any code modifications, so we didn't mess up with the checksums, and we have already patched the handle exception filter trick. So if we just see what happens, this is the function that calculates the full checksum. We don't need the hardware breakpoint anymore there. We just need we can just run basically. Until the execution comes back here. It takes a while because you see it loops for the entire section. This is also why you have to wait a few seconds while the challenge displays the data validation in progress message. It actually calculates something. So we stopped here. We see that it checks for that specific file, which doesn't exist at the moment. So we can create it. Then we see that it's going to get the file size and check if the file size is 10 hex. So we can enter. (16 bytes), which is 10 hex. Save it. So let's step in. Checks for the file. You see open existing. Finds the file, valid handle, NEX. Get file size. Okay. Indeed, I put more. That was funny. So indeed, I put 20. Okay. All right. So let me do a quick restart of the challenge. And yes, I didn't patch the handle exception filter trick again. There's a lot of stuff sometimes you need to remember, and it really messes up with your mind. So let's run. So have here 2, 4, 6, 8, 10, 12, 14, 16. Okay. So we're now basically waiting for the calculation of the checksum to end for the entire first section. Okay. Alright, so we can now continue from here. So let's enter the function, checks for the eLearnSecurity dot file, finds it. Now the size is indeed 10 hex. Then calls this function here. Okay, this is actually for the dynamic memory allocation, where it's going to read the file. So it's going to read the file here, the contents. We see that it reads the last let's go back here to see the last D word. And then XORs the last D word with the previous one. Then that result is XORed again with the second D word, and then that result is XORed again with the first D word. And then, as we see, is going to use the values from these variables here, plus the checksum calculated for the entire first section to calculate the constant that's going to be, has to be equal with this. You see, if it's not equal, it's going to zero out AL, so it's going to return 0 in AL. Otherwise, if it matches, it's going to return 1 in AL. So this is basically a Boolean function. So what we can see is that it XORs the result in ECX with this values calculated on runtime, and then that value, that let's say value on ECX, is going to be XORed with the entire with the checksum of the entire first section, and the result has to equal this, which, as you can see at the moment, it doesn't. So if we go back here, we can start reanalyzing the algorithm and see if we can find a solution to this problem to finally solve the challenge. Okay, so let's go and modify the data read from the file. So let's fill this with zeros. So you can see now that since it only performs XOR operations, we can, if we use 0 bytes here, we can only we can already predict what is going to be the last value on ECX. It's going to be the first D word only, and then it XORs that value with these values here. So let's see. XOR this value with this value here, and then with this here, and then with this here, and then with this here. So what we can do is, let's say that this value here was 0 also. Okay. So let's zero out this 6. So we need one more value that XORed with this is going to give us this result in E6. So if we fire up calculator, we can do CF6 FC 79D XOR for C8 334 25. We have this value here. So let's go back and try to see now what happens. Let's go back here. Okay, so what we have basically is that the value in E6, let's call this A, XOR B, XOR C, XOR D, call this A, B, C, D, XOR E, must equal for 8 for C8 33425. We know all these values. But we don't know this. So what we can do is to again calculate this. By 0.6. So we need the value. We know that this equals CF6 FC 79D, and so basically we want that A XOR this value here equals this. So A equals this XOR this. So we do 4C8 33425 XOR CF6 FC 79D equals this value that we found before. So if we go back here, the problem is that it reads the value using the little endian, so it reads it backwards. You see what it's going to read. So we basically just need to, it was a simple mistake, but as you see, it was enough. So we just need to change this to B8 F3 EC A3 . You see now the values match. Return is 1, and we basically solve the challenge. So the key, we can shut down Oli, and we can 0 bytes the rest. Save, run the challenge, wait for the data validation to finish, and that was it. So as you saw, we managed to solve this challenge with which contains some basic obfuscation and reversing tricks. I hope that you had fun watching this video, and I really hope that you're going to have even more fun by doing the RS course from eLearnSecurity. Thank you for watching. Have fun.